Other properties that we'll have from Calc 1 that you remember, I think today will not stop to discuss things like some general properties of continuity and for continuous functions. Composition. So composition of continuous functions is continuous. If you have two continuous functions, then the composition is continuous. One thing, if you have say well, you can start from building block with polynomial, and you plug it into, say, a sine or a cosine, then that's also continuous because of the composition of continuous functions. So, but the building blocks here are the same as once you learn in Calc 1, polynomials, trigonometric functions, exponentials, and logarithms. Inverses, inverse functions of continuous functions. Inverse functions of continuous functions. All of these are continuous in their domains. The respective domains. So as I like to put it, and this is something that I mean, it's just gonna ask you a very simple question for the discussion. So here it goes. So what is my rule here for dealing with all these expressions that you've become so used to dealing with in the past? The rule for knowing when they are continuous is to know if the expression makes sense or not. So wherever, I mean, this remark here, they are continuous in the respective domains. So if you can plug it in and that makes sense, then the function is continuous there. For instance, you take the square root of something of natural log, that's going to be continuous, provided natural log, I mean, you're taking x greater than 1. If x is less than 1, that means between 0 and 1. I mean, first of all, if x is negative, then natural log will not be defined. So, then, of course, I mean, natural log cannot be can even be continuous when it's not defined. Remember that for continuity, you need the limit to be the limit of f of x to be equal to f of c. So f at least has to be defined at the point. Now, but even then, if natural log is defined and you take a number x between 0 and 1, natural log will be negative, so you'll be taking the square root of a negative number. So then that expression doesn't make sense as it is. So the function will not be continuous. But whenever you find yourself dealing with a function composition or some expression involving polynomials, trigonometric functions, trig functions, exponentials, logarithms, and inverses of these functions. Remember, logarithm is the natural log is the inverse of e to the x. For instance, arcsine is the inverse of sine of x. So whenever you um, uh, when you have to deal with these functions, if you I mean you will immediately recognize when they are continuous or whether they are continuous or not at a given point, because if you can assign a value to the function at that point, then that means that the function is defined. If the function is defined there, then so meaning that the point is part of the domain, then the function is going to be continuous there. We're not, of course, I mean, we're not going to prove this. I mean, it's going to take too much time, and in fact, the proof of all these facts can be found in calculus books. For polynomials, it's actually very easy. It's just the same kind of, I mean, you just need to check things about the limit. So the limit of polynomials have to give you the function evaluated at the point. I mean, the polynomial evaluated at the point, but that's generalization of the rules that you also used in calculus. For trigonometric functions, things are a little bit more complicated, and the same thing for exponentials and logarithms. So the deriving that the inverses are continuous is not that difficult, provided that you know that the functions which their inverses of which their inverses are continuous. But again, I mean, this is not the point right now. One thing, but now from now on, this is, you can assume all these functions are continuous in the respective domains. That's what we wanted to get at. Now, another property that you can use from Calc 1 is the squeeze theorem. So the squeeze theorem applies also. I mean, this is just a property from Calc 1, and you also have that property here. You can apply it, and to show, for instance, this is used in, can you use as an alternative proof? I mean, it's essentially the same. You can be used alternative to the proof of the continuity of g of x equals x sine 1 over x if x is not 0, and 0 if x is equal to 0. Um, Given in example 4.3.6. So again, I mean, this is, I mean, if you remember my remark here, x and sine of 1 over x is continuous wherever these expressions make sense. So x makes sense everywhere, sine everywhere. 1 over x doesn't make sense when x is equal to 0. So this function is going to be, I mean, and since this function g of x is defined as x times sine of 1 over x when x is not equal to 0. So when x is not equal to 0, g of x is going to be continuous. So the only point where you need to actually check that g is continuous is when is the point x equals 0. And for that, I mean, you need to show that the limit of g of x as x approaches 0 is g of 0, which is 0, because I mean it's defined this way. And this limit actually exists and it's equal to 0, and this is where you actually use the squeeze theorem. Okay, so that's basically everything I have to say about these operations for continuous functions. A new part now. I mean, we finally move on to some new stuff. This functional limit. I mean, this week's material. So now we can talk about continuous functions on compact sets. So given a function f from a to r, b subset of a, f of b is the set, is defined to be the set find the set f of x such that x is in B. So that's the range of f. I mean, that's a function from B to R. Something like this. So if you have the real line and this is an interval, suppose that B is an interval, f is a function like this, then the range will correspond to the image under this function. And this is f of B here in the drawing. So the image here, and for this particular example, will contain the endpoints depending on whether or not B contains the endpoints. But this is just one drawing, one particular example. So the question that here that so this is just to give you a picture or an idea of what we're talking about discussing here. We're trying to see what can we deduce about the image of f if B has certain properties. So for instance, if B is an open set, I mean, of course everything here will the discussion here is about what kind of topological things can be preserved under continuous mapping. So f is going to be assumed to be continuous. Of course, if it's not continuous, then you can have all sorts of wild stuff happening. But if f is continuous and if B is open, can you say that the image of B under f is open? Or if it's closed, can you say that? I mean, can you say that the image is going to be closed? I'll just give you a minute to think about examples where you think, I mean, the property is true or false. So for instance, B, so we can say what motivates us is, I mean, finally something is going to be preserved by continuous function. So if you had a chance to think about the questions I asked, uh, then try to check, I mean, if your examples or counterexamples have to do with the ones I'm going to be giving now. So if B open, does imply that f of B is open. Well, the answer is no. This doesn't imply f of B is open. And in fact, it just suffices to consider any function that has, say, I mean, it's not one-to-one, it has a minimum. Say, I mean, example, x to the 2n, where n is a natural number, then if, I mean, f of x is equal to that, then the image, I mean, A, the set minus A, comma A is open, but the image of this set is the semi-closed interval 0, comma A to the 2n. Sorry about that. Now, what about B being closed? So, does B being closed imply that the image is closed? Almost. And the reason why I say almost is what we're going to present as a theorem very soon. And the reason why it fails is because there are some closed sets that are unbounded. And our example here, this is the same example what's given in the book. B closed does not imply that f of B is closed again. So what you want to have is something that can get arbitrarily close to 0, but never be actually equal to 0. So the example, which is given in the book, I mean, anything that decays as x goes to infinity will suffice. So 1 plus, give x equals to 1 over 1 plus x squared. Is continuous. I mean, remember that the function will be continuous whenever, wherever the denominator does not vanish. If the denominator is continuous, denominator is here a polynomial, so it's certainly continuous, and it's never zero because it's always positive. So now this is a continuous function, and the set b equals 0 infinity. I mean, you could have picked actually any other interval. It just has to be a semi-infinite interval. This set is closed. Set is closed. Okay, and it's not hard to check. I mean, whenever you have check of any accumulation point inside this semi-open interval. So the only way you could try to violate the fact that the limit point does not belong to the set is at point 0, but you're including that number, so the set is closed. Now the observation here is that g of b is 0, 1. The open interval 0, 1. So when x is equal to 0, g takes on the value 1. The function is decreasing, so as x gets larger, g gets smaller, and you can get arbitrarily small by choosing arbitrarily large numbers for x. So 1 over 1 plus x squared can be very, very small as you want. And so that's why you include all the positive numbers between 0 and 1, including 1, but this function can never be equal to 0. The only way a fraction can be equal to 0 is if the numerator is equal to 0, but the numerator here is 1. So we cannot include the endpoint here, and that means that the image of G, the image of B under G is not closed. But here what fails, and this is the point, this function is decreasing, so it's and so something very funny is happening. So it's getting smaller and smaller, and is approaching 0 as x approaches infinity. So problem here is that we are allowing for this kind of infinite approximation as we let the function, let this expression take on values. The argument here. So x, we are allowing it to take an unbounded, bounded possibilities. So bounded possible values for x. This will allow you to get as close to 0 as you want, and this is why you have a kind of semi-open set on this end. So the property here is that, so what fails here is not the closeness is actually very close to being preserved. So as long as you don't allow for this kind of things, then you're fine. And this is exactly the content of the next theorem, 4.4.1, which is the preservation of compact sets So f from A to R continuous you have a continuous function. That's one of the requirements, and you have a compact subset of A if both things are true, then f of K is compact. Okay, now, so then for the proof, we just go back to the definition. So what we have is we must be able to find, I mean, for any sequence inside the set, we must be able to find a subsequence that converges inside the set. Right, so we start to let yn be a sequence in f of k. So let's just put it this way. Sequence in f of k. What we want to find is a subsequence that converges, again, in the limit has to belong to f of k. Since y of n belongs to f of k, yn must be equal to f of xn for some xn in k. For all y sub n in f of k, y sub n must be f of some xn in k. It may be, you may have, I mean, you may correspond to the image of more than one point. It doesn't matter. Just, I mean, the only thing that you care about is that yn comes from someone. And this follows just from the definition of the range of f. Right? So the elements in f of a set are all the f of someone where that someone is in the set. So in this case in k. So yn must be some number of the form f of xn, where xn is again in some xn in k. And remember, xn need not be unique. I mean, unless the function is one-to-one, we cannot say that xn is unique. But we know that there's one. Now, the sequence xn has a convergent subsequence x of n k, right? Because k is compact. Because k is compact, so every sequence inside k has a convergent subsequence whose limit is also in k. Now we use the continuity hypothesis for f. So since f, this is compact. Since f is continuous, it follows that f of x and k converges to f of x. And x is in K, so f of x belongs to what set? F of K. So that is the proof. So we started with a sequence, an arbitrary sequence in the range of f, in the image of the range of f of k, the range of k, yeah, in the range set f of k, so in the image of k under f, and we were able to find a convergent subsequence. Remember we want to be more explicit now. We want to find is a subsequence of the y-n's, but this here that we're written here is exactly y sub n k, right? And we've shown that y sub n k converges to some element y, if you will, that belongs to the range set f of k, so to the image of the compact set under f. Okay, so that's a very useful thing to have. And this is what allows you to say that every continuous function on a compact set has a maximum and minimum. Remember that, and I'm just gonna make a comment once we finish writing this down. So the theorem 4.4.2 is the extreme value theorem. If f from a compact set to R is continuous, and the set K is compact, then f attains its minimum and maximum values in K, right? Inside K. And now this is an easy consequence of the previous theorem, because what is a maximum? It's a point where f, that beats every other point. So it's point x such f of x is greater than or equal to all the other values of all the values of f of y, where y is in the set K. That will be a maximum, and the minimum is value x such f of x is less than or equal to f of y for any y inside the set K. And in fact, there's some number that is an upper bound. In particular, it's an upper bound, and since it's inside the set, it has to be the supremum. So what we're asking in reality is whether or not f contains a supremum or not. So for the proof, just note So notice that, okay, so let's just define alpha to be the supremum of f over the set K. This is a limit point. I mean, this first of all exists because the image of f is bounded, right? So this thing is so the supremum exists because f of k is bounded. How do we know it's bounded? Because we just proved that f of k, I mean, if k is a compact set, then f is a compact set as well. And compact sets are closed and bounded. We already know that. So in particular, it's bounded, and so this supremum exists. Supremum exists, so it's not infinity, and this is a limit point. And it is a limit point. Remember that. I mean, we saw at the beginning of semester characterization of the supremum, and we saw that if we subtracted anything from the supremum, then we will be able to find a point in the set that to kind of greater value than that. So that means we can approximate the supremum. So as much as we want, and that's a limit point. That's what a limit point is. But since since f of k is closed, it belongs to see, I have a big delay, belongs the set. Right? How do we know that f of k is closed? Because f of k, we just proved that if k is compact, then f of k is compact, so that means closed and bounded. So a closed set is a set that contains its limit points. So the supremum of f is so the supremum of f, which is a limit point, must belong to the set. So that means it is an x such that f of x is equal to the supremum, and that means that is an upper bound for the values of all the values that f takes on the set K. The proof for the minimum is analogous. Instead of that, we just take the infimum. Okay, and that includes of course the proof. And now we we know why some theorems in calculus worked. In particular, remember that you said that if why is it? I mean, for instance, the proof of Rawls theorem. How did it go? You had a continuous function that was, I mean, you can actually strengthen it just for the sake of presenting a clean argument. Suppose that f is a continuous function in a closed interval, and it's differentiable inside the closed interval. So it continues inside, it continues on closed AB interval, so including a and b, and it's differentiable inside the open interval a comma b. So how do we know that if f of a is equal to f of b, then there is a point where f prime is equal to 0 in between a and b, strictly in between a and b? Well, if the function is not continuous, then there must be a value inside the interval that is either bigger or smaller than the values of the endpoints, which we are assumed to be equal. So now, well, just for, without loss of generality, we can assume that that value is greater than f of a, or also, okay, in terms of application, it would probably make more sense to consider the case when the value is smaller than f of a, which is equal to f of b. So that means that the function must, since the interval a comma b, including a and b, is a closed interval and is bounded, is compact, and the function is continuous in the set, set, then it must attain a minimum, and the minimum cannot be equal to, it cannot be attained at the endpoints f a and b, because you already know that there's a point that takes in a smaller value. So it has to be strictly smaller than f of a, which is equal to f of b. And at that point, so you know that because of the string value theorem. So there's a minimum, and that minimum has to be a critical point. So f prime at that point has to be equal to 0. So this is something that probably you learned in Calc 1, but it was not shown to you in this way. You didn't know why the extreme value theorem was true. So this, as I said, this allows us to recover many properties that we already knew from Calc 1. Now, very important thing is uniform continuity. Which is what comes next. And uniform continuity is defined in the following way. So it may seem strange at first, but there are some things that in our definition of continuity were implicitly dependent on other quantities, and so that's why it may look like it is the same. Well, it's actually not the case. So definition 4.4.4, the definition of uniform continuity. So a function f from a to r is uniformly continuous on a what happened here? Is uniformly continuous on a if for every epsilon greater than 0 there is a delta greater than 0, such that for all x and y in a, x minus y in absolute value smaller than delta implies that f of x minus f of y is smaller than epsilon. The reason why this may seem familiar to you because it sounds pretty much like continuity, just continuity, plain continuity, but it is not the same. So when we define continuity, we define continuity at a point, and we said that the function was continuous everywhere if, or this from Calc 1 that the function is said to be continuous if it's continuous at every point. So it's implicit there that you have a point, you're given a point, and for every epsilon greater than 0, there exists a delta. That delta depends, of course, on epsilon, but it also depends on the point x. Here, the delta doesn't depend on where you are inside the set A. So that's why it's uniformly continuous. Uniformly refers to the fact that this delta can, you can take the same delta for every point. And that's why we're talking about uniform continuity here. The uniformity here is it comes into play here, that the existence of this delta. So the uniformity refers to the fact that we can choose a delta that works for all. So it's uniform for all in all x's in the domain of f. Not all functions are uniformly continuous, but one thing that is the main objective of the next of the next lecture or the next video is to prove that if you restrict a continuous function, you have a continuous function in a compact set, then it is uniformly continuous immediately. And for instance, x squared is, which is one of the examples we'll see the next time, is not uniformly continuous. If you look at it on the whole real line, you'll see, we'll actually see how the deltas are getting smaller and smaller as we let x or number x be really large. But if you restrict it to a compact set, then x squared is going to be uniformly continuous. And so that's what we're gonna do next time. And then after that, we're just gonna go over the intermediate value theorem. We're not gonna prove it, but this is a review from Calc 1. The intermediate value theorem is a theorem which you're already very familiar with. You were tested on it many times. If a continuous function on a closed interval, takes on some value, takes on all values between f of a and f of b. F of the endpoint, both endpoints. Takes on all the values in between. This is going to be just a reminder of what you know from Calc 1. Okay, and then we're going to move on to derivatives. And just the last part. Remember, I've given you as a reading the beginning of the chapter on derivatives because it's it's a review, and we just take it from Darboux theorem, which is the only really new part. And then after that, we're gonna cover integration, which is gonna be the last topic we're gonna cover, the last chapter we're gonna be covering, and that's it for now. And then we'll talk then next time. So that's it for now. And again, contact me if you have any questions, and come to office hours if you have if there's something you didn't quite get. Okay, thank you.